We're now going to proceed our 3D demo and we're going to see how we can interpolate slash extrapolate a climatology like the World Ocean Atlas, for example, into an S-grid of an ocean model configuration. So we're going to go again in the ROMS mapping directory. We're going to open the main 3D mapping, and we're going to be looking now at tutorial number 3, which is the one that follows the loading of the climatology. So let's go in tutorial 3. Okay, and so this is the tutorial number 3. So this tutorial begins with loading the climatology. In this case, I'm going to load the World Ocean Atlas, but you can load equally the SODA dataset if you want. So let's go in our MATLAB directory. Let's go in ROMS mapping. Let's fire up MATLAB. And let's load the grid that we're going to be working with, which is the NEPD grid, the Northeast Pacific. And let's load the climatology for this grid. Okay. So here we have our climatology. And at this point, the first thing that I want to do is I want to place this climatology from its longitude and latitude to the longitudes and latitudes of the grid, grd.lnr and grd.letr. Now this of course has to be done for each depth. In this particular case, we have 32 depth, from the climatology. So I want to do a loop that interpolates, every 2D depth of the climatology into the 2D space of the model grid. Okay, so let's go in this directory here. And so what we do is we define first the length k, which is the number of depth that for which we have to do this two-dimensional interpolation, and we just call it k. Then we initialize an array that I'm going to call temp z, which has dimensions now of the grid of the model, grd.lp and grd.np, but it has vertical dimensions of depth, which is k in this case, which is the number of layers in the climatology for each particular depth. So I'm going to do this first. I'm going to initialize these two variables. Okay, so at this point I have to make a loop that for each depth k, I'm going to do an interpolation, interp2, from the longitude and latitude and the temperatures, say for example the January temperatures of the climatology, to the grid grd.lnr and grd.letr. In this case I'm going to use a cubic interpolation. Now in principle I could just provide this interpolation. In fact, let's try one of these first. Okay, so let's go and place k equals 1, and let's execute this for the first layer. So we go in MATLAB, we say k equals 1, and then we do temp equals clima.temp, and it's going to be the first layer, the first depth for the January. Okay, so I'm just doing that. So let's do that. And so I've done this interpolation, and now temp z is going to be on grd.lnr. Let's actually plot this. Let's see how it looks. P color of grd.lnr, grd.letr, and temp z of, in this case, it's just one array, so it's going to be pretty straightforward, shading flat. Now there's an error here for some reason. Temp z. Why did it do three-dimensional? Oh, because temp z was three-dimensional. We had defined it to be a three-dimensional array. We only initialized the first k, but it was a three-dimensional array. Okay. So if we look at this, we could see that in principle the temperature looks fine, but you see that there's these nan values, and this masking here is the same masking as the one from the climatology, but it's not necessarily the masking of our grid. So in other words, our grid may actually want some values. For example, if we hold on to this and we plot the coastline here, we definitely have missing values here. And so if you remember in the 2D interpolation, what we did is we used the rntfill command to extend and extrapolate in the horizontal these values all the way to the coast, so that we could actually have values for when we interpolate to our grid. So then when we do this cycle of 2D interpolation, we're going to add an additional step here, which is for each vertical layer, we're going to use the RNT fill to extrapolate the climatological temperature into the values where into the places where there's no value. Okay, so we're going to do this additional step here, and if we do this, for example, I'm going to go back in MATLAB. So the first step, we do this RNT fill, and remember these two last arguments are the decorrelation length scale in units of longitude and latitude. So this would be 3 degrees in longitude and 3 degrees in latitude. So it's a very kind of coarse extrapolation. So if we do this now for, say, for the temperature for the first, for the first K, and time equals 1. So now we do this, and if I do a peak color, and now now that I've done this, I can re-interpolate now this with this. Okay, now I'm going to again do a peak color of this new field. Now you see that it's defined everywhere, and the advantage of this is that you know, if I plot now the RNT PLCM of temp Z, comma, K, comma, GRD, now we can see that we have, you know, a temperature that is, you know, everywhere. Okay, and we saw this in the 2D. So we're going to repeat this for every single layer. And so I'm going to just do for K equals 1 to the number of layers. I'm going to do the filling of that particular layer at a particular depth, and then I'm going to interpolate onto the model grid. So I'm just going to shift the climatology from its horizontal grid to the horizontal grid of the model grid. Okay, so I'm just going to do this. And okay, there's an error here, sorry, and that's my fault, because here this climatological temperature here, what we want is not the whole thing, but we only want 2D, the layer K, and then January in this case. Okay, now to follow the progress of this, I'm going to print K as this proceeds in its interpolation. So let's go here and let's run this. So you can see it's pretty fast, and it's going to finish pretty soon. Now after I do that, at this point I have to do one last transformation, which is I have to bring this temp Z array, I have to bring it to from Z, which is in Z coordinate, to the S coordinate. And to do that, since it is already on the coordinate, on the horizontal coordinate of the model, I can use a function called RNT2S, which is basically a mapping from Z to S grid, and it wants 3 arguments. The first argument is temp Z, which is what we just did, which is this you know, this 3-dimensional temperature field at Z on the Z grid. Then I want ZR, which is the depth of the sigma layers, and we've seen what this is in one of the previous demos, and we can compute this by just using the RNT set depth routine. In this case, we use for the free surface, we use a free surface of 0, which is not quite perfect, because we would want to use a free surface which is the climatology for that month, but given that we don't have it, we're going to assume that it's 0, and given that the free surface only changes you know, about maybe plus or minus 0.5 meters in this area, it's not going to be a big deal in terms of the ZR. And then the next thing that wants as an argument is the depth of each layer, of each vertical layer, in this case of the Z grid, and so that's going to be just glima.z. Okay, so let's take these 2 lines. Okay, let's go in MATLAB. So here we finished doing this interpolation, and we can just do these 2 functions, and now I have temp S here, which is my new 3-dimensional array, which is now the temperature on the S grid. So it's actually on the model grid, and we can actually plot it. For example, in Fig, we can make a plot. For example, again, we could start by looking at the free surface, at the surface of this. In this case, because it's an S grid, the surface value is going to be grd.n. And we can see that this is identical to that. If we plot the bottom value, what we should see is, of course, something that looks like this, where here, where this S coordinate is becoming shallower, the temperature is warmer, okay, and when it's deeper, it's cooler. So that's kind of typical. Now we can actually look at a section, for example, a vertical section. We can use the command RNT sect x of temp S, we're going to take a section along the I index equal, say, 60, and then we're just going to give GRD. And you can see that now you have your your temperature field, that it looks something, like that, warmer at the surface, colder. So this is, we actually devoted, in fact, actually, if you do shading, I think flat here, actually, no, this doesn't work. Anyway, this is, what I'm saying is that we can actually run this command and have it return some inputs like P1, let's say actually X, Z, and then the field. Actually, this routine will return that for you. Okay, so it plots it. Now I can clean it, and I can use pcolor to just replot that field, ZF. And so now you can see, in fact, the sigma coordinate, how this is actually on the sigma coordinates. You can zoom on, um, in a particular region, say here. And you can see now how it's discretized on the S coordinate, and so you can see that now this, if I do a shading interp, it looks kind of more smooth, but the reality is that that it's on an S grid right now, and so this is the actual grid where the temperature is on the new grid. Now, as a last step, once you have that, in principle, if you're producing some files, you may want to store this array, temperature S, or any other array, the salinity, the velocity, whatever you're working with. You may want to save it into a climatological file. And so here is a function rnc create clima file, which will create a 12-month climatology file for the model. In this case, this file will contain the temperature, salinity, and all the different arrays needed from the model. And it's going to do that by just taking information on the GRD array. And it's taking some time. And in fact, if we do an nc dump of this file here now, we can see that it has all the various dimensions that it took from the GRD. It has 12 values, and it has this sea surface height, the zeta, SSH, and so forth. It has all the values that you need. Okay, but in this case, this is an example, so the only thing that we have is the temperature. So we're going to create a CTL now of this particular climatology file by just doing that. And the problem is that I had to initialize the variable file, which I'm going to do right now. Okay, so here I'm going to initialize this variable, and here, since I have a variable now, I'm going to use the variable name instead. Okay, and I'm going to save that. So now that I have the variable initialized, I'm going to go back here, paste it, and then I'm going to create the CTL for this file. Okay, it gave me an error here, and okay, so now we have 12 months there. So here I have to tell it the calendar. I forgot to tell the calendar. Okay, and now I can use the rnt save var command, which you've seen before. CTL is the CTL of the climatology. I want to write January record, I want to write temperature, and I want to write temp s, which is the one that I just created. So now I can just paste this in here, and I basically now have the temperature stored in the netcdf file. And I can go further down here. Let's see, if I look for temp, you can see that now the January temperature is actually has some values in it. Okay, so this is all for interpolating, with this interpolating the climatology into the S grid of the model. And you can think of writing a script that does this for every single variable and so forth. And in fact, later we'll see such a script that we will use to create the entire files. But this is just a proof of concept of how you would do this. So the first step, again, is you do a 2D mapping onto the model grid for each layer. You use the RNT fill to kind of assign values where you don't have values, especially close to the coast. And after you have this this stuff on the model grid for each vertical layer, vertical depth I should say, then you do a transformation, a mapping from the Z grid to the S grid, this stretch coordinate system using this function rnt to s. So this is all for this demo. Thank you.